Hello everyone, I am Argadeep Das and today I am going to talk on the research paper towards federated learning at scale system design. So it has about 14 authors. That is the longest list of authors I have ever seen for a research paper. This paper was presented at SysML conference at California in 2019 and all the authors are from Google. So before we begin, let's have some background and understand the importance of this research paper. So why not simple machine learning? Well, it has always been the traditional approach to bring the data to our code. That is, we write the code for training a model, we plug in our data, and it trains the model. So, what is the harm in this? Well, bringing the data to the code means that we need to collect all the data, centralize it, and store it at one place. This makes it vulnerable to getting exposed by security threats. And in recent decade, we have seen the abnormal rise in data leaks that is happening almost every week and every other day some or the other company is being a victim of data leak. This has jeopardized the user privacy and has caused various companies to lose their market because they are unable to protect the user privacy. So, is there a better approach to this? Can we bring the code to the data? Is it possible? Yes. This is what is known as federated learning. By bringing the code to the data, it helps in addressing the fundamental problems of privacy, ownership, and locality of data. So, till date, we have been relying on the centralized scheme of ML systems. That is, different users will send their data, it will get collected in one place, and then the model gets trained. However, in decentralized scheme, the server will not be collecting the data. Instead, it will send the model copy to each and every device, run that model on the user device itself, and whatever is the output, it is encrypted and sent to the server, and then the server will accumulate all such encrypted results and then improve its model. So what it does is it puts the privacy at the hands of the users itself and helps them to maintain their secrecy while still ensuring that the model is training accurately. So, as we jump into the contents of this paper, we will begin with the introduction. So, there are basically two types of federated learning, that is asynchronous and synchronous. Till now, the conventional way of distributed training in synchronous training is that, for example, if we take stochastic gradient descent, in that each worker will get typically bind to a GPU device. It will process a partition of the mini batch, calculate the local gradients, synchronize those gradients with other workers, and then apply gradient to its local copy before processing the next mini batch. So what it does is every worker will update its own local copy, and then finally they will update the global model and repeat. In asynchronous, the models are trained on the devices and then they are combined into a supermodel, and this process is again repeated. Now, there are two important ideas that are key to this paper. So, the first is differential privacy. Our datasets and models should not indicate any information specifically about me. It should have at least epsilon uncertainty about me. So, for example, if I'm sending a data that it is about me, for example, if it's a patient, my medical history data, I do not want the hospitals to know that it is my data, but my data should be useful to them in order to train their model for better prediction of any disease. So, differential privacy will ensure that my data is being used without compromising my privacy. Another concept is secure aggregation. That is, the information which is sent by the device should not reveal anything specific about me. So, in secure aggregation, my results are encrypted and then sent to the server, and the server can only decrypt the aggregate result. So, for example, if I am sending my data and thousands of other people are sending their data, the data is sent in an encrypted form whose key is not available with the server. The keys are present with the user themselves. The server can only see the result of combining these encrypted results as a whole, but it cannot break down individual components and see as to whose data it is. So, differential privacy, as we talked about it. So, for example, in this comic, you can see that the data point that has come is very unique, and the model is trying to prioritize it. So our goal is to ensure that a model is not particularly biased towards memorizing something special. So this is when differential privacy is brought in. That is, it is able to measure and control how much a model should be memorizing. So by being able to add noise to the data, we can now see that the data is in an obscure form, and hence this has reduced the speciality of that data, and hence the model can no longer be biased towards it. Another thing that we discussed is secure aggregation. So one question that comes to mind is, if I am sending my data to the server, is there any way it is possible to combine the data and reverse engineer it to find more information about me? Can it be reverse engineered in such a way that my information gets exposed? Well, no. Secure aggregation ensures that the data is encrypted and then sent to the server, and the key of that encryption is only available to the user and not to the server. The server can only see a combination of these encrypted results and decrypt the aggregate. So now here is a very interesting question. You have to make a system that trains on data that is spread across hundreds of millions of devices spread across the globe, right? So there are different devices across the globe, different time zone, everything. People use phone at different times. They are in, they have different sleep patterns, everything. All this has to be accounted. So is it possible to achieve a model training in one run? So this is the level of competence that Google has to deal with daily. So let us look at how they plan to take up this challenge. Before starting with any such problem, we need to understand the design challenges. So the first is device availability, internet connection, and a thousand other technical reasons. For example, why you want a new phone or a new SIM. After the collection, the next design challenge will be orchestrating the training. Everyone is using the device at different times. When is the right time to collect the information and everything? And after you're done with the collection, how will you orchestrate that training in such a way that it is a continuous process? Third is scalability. How will you scale your algorithm in such a way that you do not experience much downtime or do not experience a catastrophe while trying to train your models? And finally, is the resource availability for training in such a dynamic environment. So now it's time to put on some thinking cap and think about system design, but at Google level. So we will now look into the protocol and system design overview. So in order to better understand the system architecture, it is best to start from the network protocol. So before starting with that, we will understand some basic notions. So the participants in the protocol are Android devices, and there is one FL server, which is a cloud based distributed service. So the devices will announce to the server that they're ready to run an FL task for a given FL population. So an FL population is basically a global unique name which identifies the machine learning problem that you're trying to solve or which is being worked upon. For example, understanding your keyboard suggestions. Whenever you type something, your Google keyboard suggests words. So understanding your typing pattern, that is a machine learning problem. So that problem will be called an FL population in this paper. An FL task is basically a specific computation for one FL population, such as the training to be performed or evaluation to be done. So now we will try to understand the flow of one federated learning cycle. So it has three phases, that is selection, configuration, and reporting. In the selection phase, you select a few more devices than you actually need. So for example, you have chosen thousands of devices, but for the one cycle, you only choose few hundred of them. Remaining are sent a notice that okay, we are not able to take you in this batch right now. We will give you a later schedule and please be ready at that time. This is what is known as space steering. It enables the FL server both to scale down to handle small FL population as well as scale up to very large FL population. The pace steering is based on the simple mechanism of the server suggesting to the device the optimum time window to reconnect. The device attempts to respect this given its eligibility. Next is configuration. So, whenever the devices are ready to be in contact with the FL server, every device is sent an FL plan. So, that plan can have the model, the functions, metrics, etc. All those information is sent to the devices which have been chosen for that round. and then that plan gets executed on all those devices. Finally is the reporting stage. Once that plan is executed, the device will now send the updates and stats back to the FL server. The server will collect all these data from different devices and aggregate them. So now, as you can see, whatever we discussed, it is present in the form of an image. So in the first stage, you can see that the devices are checking in with the FL server, and the rejected ones will have to come back later. Then in the configuration stage, the server has sent an FL plan for training, whereby all these selected devices are running the training on the devices. And in the next stage, that is the reporting stage, they have sent their own encrypted data, and then it is getting aggregated and sent back to the server. Then again in next round, all those devices which were rejected will now again try, and if they get accepted, they will again do the same process, and this will carry on. So now another thing that we need to think about is, if we are performing such heavy computations on the user side, so how much is the user getting affected because of this? Because machine learning is an intensive process and it requires computation power. Utilizing people's mobile for training can cause problems for the user. The utility of the mobile may go down. So this is also another challenge that has to be kept in mind, that the user should be happy and they should have minimal impact or not even come to know that some training is going on the device. So in order to ensure that FL processes are run on devices that are idle or connected to Wi-Fi or currently being charged, because these are assumed to be those states where the mobile is idle and you're not impacting the user. All these processes are getting scheduled by the Android job scheduler, and the training has the lowest priority. In the device side computation, as you can see, for example, an app is carrying out a process. So let's take an example of Google Keyboard. So what Google Keyboard does is, whenever it is running the FL process, it has to store the results of the model training in what we call an example store. Whenever the FL server will request for the information, the FL runtime will run and it will ask for data from the example store and send it to the FL server as a model update. And whenever the FL server has to tell the device that it needs to execute an FL plan, it will send that FL plan again to the same FL runtime, and then it will get computed using the app process. So it's a continuous to and fro process. That is, if the server is instructing that the model has to be trained, it sends that FL plan, it gets executed on the device. The device will then send the update back to the FL server about the model training completion or evaluation. Let us understand some of the important device side operations that are taking place. So first is job invocation, that is job for the FL is started. It connects to the server and verifies whether any FL task is needed. If yes, it executes the same or sleeps until the next invocation. Next is task scheduling. This involves computing the plan using stored examples. Then reporting. This will involve basically reporting the data back to the server whenever the task is completed. Next is multi-tenancy. This basically means that you are supporting training of different FL populations in the same app or multiple apps. So basically, it is not just one FL population that can run, you can have multiple FL populations running on the same device. This allows the various training operations to coordinate between themselves and assure that the device trains only one instance at a time. And finally is attestation. This allows the devices to be connected to the FL server anonymously. Because as we started with privacy, that is the key concern of this paper. So using Android self-attestation, it allows only legitimate phones to connect and not revealing any user data. Now let us look at the challenge on the server-side computation. The server has to be so flexible that it can scale from 10 devices on testing to 1 billion devices on deployment. So loads and network traffic changes from location to location and different time zones. So everything is very dynamic. The dynamic learning has to take place in this distributed cloud environment. So the solution to this comes from the fact that treating everything as an actor. So actors are strictly sequential processes which use message passing to coordinate between them. So in this way, parallelism is obtained by running and creating multiple actors in parallel, and these actors will then help in coordinating between them. Since they are all copies but running different processes, the coordination becomes really easy between them. Coordinators which allow global synchronization and sub-actor management. So for every FL population, there is one coordinator. Now we talk about selectors. They are responsible for communicating, coordinating, and selecting the devices. They receive communication from coordinator about how many devices it should allow, when to forward to aggregators, etc. They are more close to the user devices than it is to the server. Next, we talk about aggregators, which aggregate data from selectors placed globally. So maybe there are multiple selectors for, you can say, multiple regions. What aggregators will do is that they will combine the results of multiple selectors together, and different aggregators will store information for a larger region. And finally, we have a master aggregator. So master aggregators will aggregate data of all aggregators. So as you can see, this is like a hierarchy. From selectors will collect from devices, aggregators will collect from the selectors, and then master aggregator will collect everything from all aggregators. And since all these operations happen in memory, these ephemeral actors are improving scalability by removing the latency, which is normally incurred by distributed storage. And since it is happening all in memory, no logs are kept, and hence they are not vulnerable to external attacks. So as you can see in the diagram, as we discussed, the selectors are getting responses from the devices. Then it is forwarding those information to the different aggregators, and then those aggregators are passing on to the master aggregator. The coordinator had created the master aggregator, and the coordinator also coordinates with different selectors about when to send information to devices. But now, how do we know that our FL processes are not affecting the users and if our model training and everything is going fine? So, for that, we need analytics. We take log and metrics to ensure that our users are not getting affected. When we think of applications of federated learning, it's already prevalent in the industry, and it is maybe already in your phone and you probably don't even know it. So let us look at some examples. First is on device item ranking. This is especially used for in app lists and recommendations. So for example, in Android 10, whenever I'm using certain apps, so for example, when I open WhatsApp or Instagram, so model will identify a pattern that whenever I open WhatsApp, after a few minutes, I often open Instagram or Twitter. So my mobile is trying starts identifying that pattern, and whenever I am in the all app mode, it shows me that whenever I open WhatsApp, these are the most opened apps, and maybe I want to open these. It puts all those most opened apps with WhatsApp at the reach of my fingers. So this is on-device item ranking. Next is content suggestion for on-device keyboard. So this enables recommendation for search queries and other input feeds. So this it is also used to rank various suggestions, and as we discussed that it is being used in your Google keyboard very actively. Next, word prediction. So this method uses recurrent neural network for these operations, and this RNN was trained using federated learning in Google keyboard. So this Google keyboard example is a very popular example of federated learning. That is, you have a universal server for this, which is a distributed cloud-based server. However, all the models are running on the local devices, and it is giving you personalized suggestion without actually storing your data at any central server, but the data stays at your device only. So the overall general statistics which they reported was that 75% devices were able to complete their entire cycle. Around 22% devices are rejected when the updates are received, and about 2% had their execution interrupted, maybe because some people even operate their phones at night, or suddenly they wake up and want to check their phone, etc. So what does the future hold for federated learning? Well, bias is a very important factor that is to be addressed in future, and the bias data of user creates bias model. With more addition of data, there will be slower convergence. Another challenge will be device scheduling should consider users and their data. Another thing, exhaustion of Wi-Fi. Federated computation is coming soon, especially in analytics. So the references for this paper, that is the paper itself, and the amazing comic on federated learning by Google themselves, which helped me understand the concept of federated learning very easily. So to conclude, till date it was believed that data to code approach is the only way. However, recent data breaches have forced people to think of alternatives such that the user's privacy is always preserved. Personal data protection is really important. but that doesn't mean AI can't get smarter using it. Thank you.